Swayam Prabha. Digital India. Educated India.
I welcome you all to lecture number 9 on the topic dual combustion cycle, which is another air standard cycle which we are going to discuss in this class. Before having a look at the dual combustion cycle, let us have a small recap what we have seen in the previous lecture number 8. We have seen the various processes of a diesel cycle, how to plot this process on a pressure volume diagram, temperature entropy diagram. If you compare the processes of a diesel cycle with an Otto cycle, primarily there is only one difference, that is in process number 2, process 2 to 3, that is the second process. In case of an Otto cycle, the heat is added at constant volume, whereas in case of a diesel cycle, it is added at constant pressure. Whereas the other three processes remains the same. 1 to 2 is isentropic compression, 3 to 4 is isentropic expansion, and 4 to 1 in both the process, the heat is rejected at constant volume. And we have seen the compression ratio, how does it vary in case of a petrol engine and a diesel engine. For a petrol engine, it is a range from 6 to 12, will take from 8 to 12 or 6 to 12, and for a diesel engine it is from 12 to 20. The higher compression ratio for a diesel engine is higher than the petrol engine. And we are familiar with the working principle of the SI engine and the CI engine. However, in practice there are significant deviations from the ideal cycle because the working fluid is in the ideal cycle is considered as a ideal gas. The CP, the specific heat, does not change, it does not vary, it is a fixed one. The combustion process is replaced by a heat addition process, exhaust process is replaced by a heat rejection process. And if you compare the ideal diesel cycle and the actual cycle, in ideal diesel cycle the heat is added at constant pressure, whereas which is very difficult to maintain in the actual practice. Similarly, in an Otto cycle, maintaining a constant volume during heat addition process, for that to happen the combustion has to be very rapid without any change in the volume or without change in the pressure in case of a diesel cycle. So because of these challenges, this incorporating an ideal cycle in the real time practice is not possible. Now let us see the various processes of a dual combustion cycle. This cycle is unique in a way in two senses. First one is most of the thermodynamic cycles have 4 processes, 1 to 2, 2 to 3, 3 to 4 and 4 to 1. This cycle consists of 5 processes. Let us see the process one by one on a PV diagram and TS diagram. And second thing is even with much deviation from the ideal cycle, this cycle exists only in theory, it does not in real time practice. Let us see the pressure volume diagram, the temperature entropy diagram, simultaneously the processes of a dual cycle. The dual combustion cycle is also called as a dual cycle. It is a combination of Otto cycle and diesel cycle, especially in terms of heat addition, process. It is a combination of both Otto cycle as well as diesel cycle. Like the previous two air standard cycle, we will derive the thermal efficiency or the air standard efficiency of the dual cycle and one numerical question to conclude this lecture. So let me plot start with the process. So like the previous two air standard cycles, I will simultaneously plot as I explain the process one by one. So first let me draw the PV coordinates, pressure and volume, and on the right hand side I am having temperature and entropy. Okay. So there are 5 processes, so this is a very unique cycle. Let us first process, there is no change in the previous 2 cycles as well as this cycle, isentropic compression. So, isentropic compression. So, this is on a TS diagram, isentropic compression. So, we know during the compression process the pressure increases from P1 to P2. So, this is P1, this is P2, so this is P1, the volume is here is V1 and here the temperature is T1, here the temperature is T2. Because it is a reversible adiabatic process, the entropy remains constant. So, S1 is equal to S2, S1 is equal to S2. Okay. So, this is process 1 to 2, isentropic compression like Otto cycle and diesel cycle. Next one is 2 to 3, constant volume, first heat is added at constant volume. Here heat addition takes place in 2 stages. Heat addition is first added at constant volume, then heat is added at constant pressure. So, this is the speciality of this cycle. So, that is why it is a combination of Otto cycle and diesel cycle in terms of heat addition, because in Otto cycle the heat is added at constant volume, in diesel cycle the heat is added at constant pressure. So, in dual cycle, combustion cycle or dual cycle, heat is added both first at constant volume. So, partial amount of heat is added at constant volume and the remaining heat is added at constant pressure. So, 2 to 3 and 3 to 4, constant pressure is line perpendicular to y axis. Okay. So, during both these process, Qs is the amount of heat supplied. So, here this is constant volume heat addition and this is constant pressure heat addition. Okay. So, this is 2 to 3, this is 3 to 4. Volume equal to constant, here pressure is equal to constant. In both this process, Qs is the amount of heat added. Okay. So, 2 to 3. So, there is one heat addition which takes place at partially at constant volume and partially at constant pressure. So, this is what is the next process 2 to 3. See, both are heat addition process, both are heat addition process, constant volume. So, 3 to 4. In the previous 2 cycles, 3 to 4 is isentropic expansion, the expansion starts, but here it is the number of processes are 5 instead of 4. So, the expansion starts at point number 4, not at point number 3. So, this is expansion process 4 to 5, 4 to 5. So, here it will be line, the curve, the shape of the curve will be, trend of the curve will be similar to 1 to 2. 1 to 2 is compression. Okay. So, this is isentropic expansion 4 to 5. So, 4 to 5 is isentropic expansion. Now, as we know the thermodynamic cycle, the initial state and the final state should be same. So, it has to be completed process, there is one more process 5 to 1, then only it becomes a thermodynamic cycle. So, 5 to 1 is constant volume heat rejection. So, heat is rejected at constant volume like previous to gas standard cycle, that is Otto cycle and diesel cycle. So, volume is equal to constant. So, here the line will be perpendicular to x axis. So, this is 1. So, this is the heat rejection process QR. So, V1 volume at 1 is equal to volume at 5, volume at 1 is equal to volume at 5. Okay. Volume at 2 will be equal to volume at 3, because 2 to 3 is constant volume heat addition. Then pressure at 3, if you extend this line, pressure at 3 will be equal to pressure at 4. So, the maximum pressure occurs at point 3 and 4, that is P3 equal to P4. It occurs at 3 or 4, both are same. So, this is the maximum pressure that occurs in the dual combustion cycle, and the maximum temperature is T4. maximum temperature may be T3 or T4. Okay, so because this is the maximum temperature, because first heat addition is from 2 to 3 constant volume, then from 3 to 4. So, 0.4 is above 3. Okay. So, this is the maximum temperature. Let me extend this line because so this is this one entropy, because 4 to 5 is isentropic process, like similar to 1 to 2, entropy at 4 is equal to entropy at 5. Entropy at 4 is equal to entropy at 5. So, now here which are all the properties at various states remains constant is volume at 1 is equal to volume at 5, volume at 2 is equal to volume at 3, because both are constant volume process, and pressure at 3 is equal to pressure at 4, pressure is equal to constant. So, these things have to be kept in the mind when we derive the air standard efficiency of the dual cycle, air standard efficiency of the dual cycle. So, this is the summary of the 5 processes in the dual cycle. 1 to 2 is isentropic compression, 2 to 3 and 3 to 4 are heat addition, 2 to 3 is constant volume and 3 to 4 is constant pressure, 4 to 5 is isentropic expansion and 5 to 1 is constant volume heat rejection. So, in all the 3 air standard cycles which we have seen so far, Otto cycle, diesel cycle and dual cycle, the heat is rejected at constant volume. There is no change in that process. Only the heat addition process takes place at different, there is a difference in the heat addition process only. In case of Otto cycle it is constant volume, in case of diesel cycle it is constant pressure, in case of dual cycle it is first at constant volume and second at constant pressure. With this background, let us derive the air standard efficiency of dual cycle. Okay. So, let me draw the diagram also so that it will be helpful. PV diagram, because this efficiency derivation is very important. If you are able to understand this the derivation, then it becomes easy for the numerical question. Any type of question which are given, we can easily solve it. So, this is 1 to 2 constant volume heat addition, 2 to 3, then constant pressure heat addition, 3 to 4, then okay. So, let me extend this line. This is point number 5, this is 1. Okay. So, you can see the arrow mark, it is moving in the clockwise direction. So, as I mentioned before, all the power producing cycles will have arrow mark in the clockwise direction on the PV diagram or on the TS diagram. So, let us mark here V1 equal to V5, volume at 2 is equal to volume at 3, this is pressure at 2, and this is the maximum pressure in the cycle, P3 is equal to P4. Okay. Whereas, volume at 4 is different, volume at 4 is different, volume at 2 and 3 are same. Similarly, volume at 1 and volume at 5 are same. Pressure is same only at 3 and 4, pressure is same only at 3 and 4. So, this is the PV diagram. So, TS diagram, this is temperature, entropy, this is isentropic compression, constant volume heat addition, 2 processes are there, then isentropic expansion. So, this will be 3, 2 to 3, 3 to 4. Let us mark the QS also. See, these are all these things have to be marked. By looking at the PV or TS diagram, one should be able to tell where the heat is added, where the heat is rejected, which property remains constant at which state point, pressure constant at which state point, volume is constant at which state point, entropy is constant at which state point, everything should be clearly marked, and the arrow mark is very important. So, this is 5, okay. This is 5. So, during process 2 to 3 and 3 to 4, QS is the amount of heat added, and here volume equal to constant, here pressure equal to constant, here volume again is equal to constant, and during the process 5 to 1 QR is the amount of heat rejected. So, here during 2 to 3 and 3 to 4 heat is added and 5 to 1 heat is removed. So, it should be the arrow mark should be pointed towards the right side. Okay, it should be away from the system, not into the system. Heat is removed from the system. So, this is the maximum, this is the maximum temperature. Okay. So, now let us define the air standard efficiency or thermal efficiency. Output by input, W net by heat supplied, that is QS. W net is heat supplied minus heat rejected divided by heat supplied. So, divide the numerator and denominator. QS by QS is 1 minus QR divided by QS. So, this becomes equation number 1. Let us substitute the value of QS and QR. QS is, as we know, heat is added in two processes. One is 2 to 3 and another one is 3 to 4. 2 to 3 is constant volume. So, CV into delta T plus heat is also added constant pressure, Cp into delta T. So, this is nothing but Cv into delta T, constant volume is 2 to 3. So, T3 minus T2, T3 minus T2 plus constant pressure is 3 to 4. So, Cp into T4 minus T3. So, this is constant volume process and this is constant pressure. So, T4 minus T3. This is the heat addition. Heat rejected is, heat is rejected during the process 5 to 1, 5 to 1, during which the volume is constant. So, you have to write Cv only into delta T, that is higher temperature is T5, lower temperature is 1. So, Cv into T5 minus T1. So, let this be equation number 2, this be equation number 3, equation number 3. Substitute equation 2 and equation 3 in equation number 1, in equation number 1. So, therefore, thermal efficiency is equal to 1 minus, instead of QR substitute equation 3, Cv into T5 minus T1 divided by, instead of QS, two terms are there, these two terms have to be substituted, Cv into T3 minus T2 plus Cp into T4 minus T3. So, we can put a you can put a square bracket also. Okay. Now, divide the numerator and denominator by Cv. Divide the numerator and denominator by the term which is inside the bracket, divide by Cv. So, we get this Cv and this term will get cancelled. Okay. So, here I will get Cp by Cv. So, that will be equal to, so you can see this one. Okay. So, we will get 1 by gamma, 1 by gamma. So, Cv and Cv will get cancelled, here also Cv and Cv will get cancelled. So, 1 minus T5 minus T1, the Cv term will get cancelled divided by this denominator Cv also will cancel, T3 minus T2 plus Cp by Cv is gamma, ratio of Cp by Cv is gamma. So, gamma into T4 minus T3. So, this will be equation number 4, equation number 4. So, So, 1 minus T5 minus T5 in the denominator T3 minus T2 plus gamma into T4 minus T3, the CV term get cancelled. So, this will be equation number. Now, I am going to define the compression ratio, okay. R is the compression ratio, V1 by V2, okay. So, compression ratio is the volume before compression and after compression, that is V1 by V2. Cutoff ratio here is, the symbol used is R suffix C. In the diesel cycle it is V3 by V2. Here cutoff takes place at point number 4, between point number 4 and 3, not 2 and 3. 2 and 3 is constant volume heat addition. Here cutoff is during the constant pressure process. In the diesel cycle constant pressure process is 2 to 3, whereas in a dual combustion cycle the constant pressure process is 3 to 4. So, V4 by V3 is the cutoff ratio, V4 by V3. In case of diesel cycle it is V3 by V2. Okay. So, there is one more ratio which we are going to define is pressure ratio, okay, P3 by P2. See, because if you see during the process 3 to 4 pressure is constant, but if you compare the pressure at 2 and 3, okay, there is a significant increase in the pressure. So, P3 by P2, that I am defining as pressure ratio, pressure ratio, R suffix P, R suffix C is cutoff ratio, R suffix P is pressure ratio, R is compression ratio. So, P3 by P2, P3 by P2. So, these three ratios will be used in the derivation, Okay. So, that is what I have explained here, compression ratio, cutoff ratio and pressure ratio Now, let us consider the process 1 to 2. See, if you see the equation number 4, okay, we have got all the temperatures T1, T2, T3, T4, T5, okay. So, sorry, equation number 5, because we have divided the difference between equation number 4 and 5 is we have divided by CV term. So, CV term gets cancelled, only Cp by Cv is gamma. So, we have got 5 terms, 5 temperatures and 1 gamma. Like the efficiency of the diesel cycle, where we expressed T2 in terms of T1, T3 in terms of T1, T4 in terms of T1, so that the term T1 gets cancelled. A similar procedure to be adopted here also to simplify the air standard efficiency. So, consider the process 1 to 2, process 1 to 2, 1 to 2 is isentropic compression, it is isentropic compression or reversible adiabatic process. So, as I said before, for a reversible adiabatic process we can use the relation, you can use the relation in which gamma is involved, isentropic compression. So, T2 by T1 is equal to V1 by V2 whole power gamma minus 1. Again, the reason why I am writing the temperature T2 temperature ratio T2 by T1 in terms of V1 by V2 is because V1 by V2 is the compression ratio which is expressed as R. So, we can easily substitute instead of V1 by V2 the compression ratio. So, this is nothing but R. So, this is R power gamma minus 1. Therefore, T2 is equal to T1 into R power gamma minus 1, okay, R power gamma minus 1. So, this will be equation number 5, equation number 5. So, that is what I have shown here, T2 equal to T1 into R power gamma minus 1. So, I have given one more equation number. So, that is why it is 6 here. So, okay. Now, let us consider the process 2 to 3. So, here I have expressed T2 in terms of T1. So, next I will express T3 in terms of T1 and similarly T4 and T5. Okay. So, to express the temperature T3 in terms of T1, consider the process 2 to 3. If you recollect the process 2 to 3, 2 to 3 is constant volume heat addition. the volume at 2 is equal to volume at 3, volume at 2 is equal to volume at 3. So, V equal to constant. So, write the basic equation P2 V2 equal to R into T2, P3 V3 equal to R into T3. See, if you know equation directly we can write, in case if you are not able to recollect, we can use this one and it is a very small derivation. Divide this equation, the first by the second equation or second by the first, ultimately you will get the same expression only. R term will get cancelled, volume is constant, so V2 term will get cancelled. So, P2 by P3, P2 by P3 is equal to T2 by T3, P2 by P3, or in other words, okay, let me write it here, T3 by T2 is equal to, I am bringing the term T3 in terms of T3 by T2. So, that will be this P2 by P3, this pressure ratio will move to the right side. So, P3 by P2. This P3 by P2 is nothing but pressure ratio, this is nothing but pressure ratio. So, this is nothing but R suffix P. Now, T3 is equal to product of T2 into pressure ratio. Now, I have expressed T3 in terms of T2, but my aim is to express T3 in terms of T1 because I have expressed T2 in terms of T1. So, nevertheless, we can express the temperature T1 also in terms of T2, 3, T3, T4, T5, everything in terms of T2 or other temperatures, but it should be uniformly expressed, whether it is in terms of T2 or T3 or T1, it should be consistently maintained. So, now T3 is in terms of T2. Now, I am going to use equation 5. So, using equation 5, because T2 in terms of T1, therefore, T3 is equal to, instead of T1 I will substitute, instead of T2 I will substitute T1 into R power gamma minus 1 multiplied by pressure ratio. So, this is equation number 6. So, have a look at the equation number 6. T3 is expressed in terms of T1, compression ratio, gamma and pressure ratio, So, out of 5 temperatures, T1 is I am keeping as it is, T1 I am keeping as it is, T2 is expressed in terms of T1, now T3 is expressed in terms of T1. So, we have to express T4 and T5 in terms of T1. Here there are 5 processes, so there are 5 temperatures are there. Okay. So, this is what, let me see this one. See, T3 in terms of T1 into pressure ratio into compression ratio power gamma minus 1. So, here it is equation 7, for us it is equation number 6. Now, let us go to the process 3 to 4. Let us go to the process 3 to 4. Consider the process 3 to 4. 3 to 4 is a constant pressure process. So, write a similar relation. Process 3 to 4. So, it is also quite a lengthier derivation, slightly lengthier than the diesel cycle, but we will try to finish it within the time and a numerical question also. So, 3 to 4 I am writing pressure is constant, during this process pressure is constant. So, P3 V3 equal to R into T3, M is taken as 1, P4 V4 is equal to R into T4. Divide the first equation by second equation, or you can write the other way also. First you can write P3 V3, P4 V4 equal R into T4. Similarly, P3 V3 equal R into T3. Okay, R will get cancelled. The pressure term also will get cancelled because P3 is equal to P4. You can see in the diagram also, P3 is equal to P4. 3 to 4 is a constant pressure process. So, V3 by V4 is equal to T3 by T4. My aim is to find out T4 in terms of T1. So, let me bring this one like T4 by T3 is equal to V4 by V3, just I am writing the reciprocal. Okay. T4 by T3 is equal to V4 by V3. Now, what is V4 by V3? This V4 by V3 is nothing but cutoff ratio. cutoff ratio. The cutoff ratio in a diesel cycle is V3 by V2, whereas in a dual cycle it is V4 by V3, because the heat is added at constant pressure during the process 3 to 4. So, this is cutoff ratio. So, this is nothing but cutoff ratio R suffix C. Therefore, T4 is equal to T3 into cutoff ratio. Here I have got T2 in terms of T3 in terms of T2 and pressure ratio, which I expressed in terms of T1. Here I have got temperature at 4 in terms of cutoff ratio and T3. Already we have expressed T3 in terms of T1. So, now using equation 6, this T4 will become T1 into R power gamma minus 1 into pressure ratio into cutoff ratio. So, this will be equation number 7. Let me repeat, T4 is equal to T3 into R suffix C, that is cutoff ratio. I am going to use equation number 6 to replace T3 and express T3 in terms of T1 compression ratio and pressure ratio. So, this is equation number 7. So, that is what I have got here. T4 equal to T1 into compression ratio to the power of gamma minus 1 into cutoff ratio into pressure ratio. So, now we have expressed T2, T3, T4 in terms of T1. The only temperature which is left, which is yet to be expressed in terms of T1 is T5, that is. So, this is process we have considered 3 to 4. So, next we will consider the process 4 to 5. 4 to 5 is isentropic expansion process. Just see the 4 to 1 is isentropic expansion process. So, entropy is constant, entropy at 4 is equal to entropy at 5, 4 to 5. So, I can write that relationship like T2 by T1 equal to V1 by V2. So, consider the process 4 to 5, write the relation between T5 by T4, T5 by T4, T5 by T4. If it is T5, if you are writing the relation between temperature and volume, if it is for 5 means it will be 4, 4 means it will be 5 whole power gamma minus 1. Okay. So, V4 by V5 whole power gamma minus 1, V4 by V5. Now, look at the pressure volume diagram. What is V5? V5 is equal to V1, V5 is equal to V1, because process 5 to 1 is constant volume heat rejection. So, but V5 is equal to V1, since 5 to 1 is constant volume process. Okay. So, therefore, T5 by T4 is equal to V4 by V1, V1 whole power gamma minus 1. Okay. So, like the previous one, multiplied the and divide the right hand side, the previous equation by V3, Okay. So, multiply and divide by multiply and divide the right hand side of the previous equation, which is by V3 by V3. Therefore, T5 by T4 is equal to V4 by V1. I am multiplying by V3 and divide by V3, so that the right hand side remains unaltered, gamma minus 1. Now, I will club this V4 and V3. What is this V4 by V3? V4 by V3 is cutoff ratio or C. So, this is equal to, I will write, okay, let me write one more step, V4 by V3 into V3 by V1, okay, into V3 by, okay, V3 by V1, correct. What is V3? V3 is nothing but V2, because process 2 to 3 is constant volume. So, this can be written as V4 by V3 into this V2 I will write as V2, this right, okay. So, therefore, T5 by T4 is equal to, okay, so I am writing it here, T5 by V4 by V3 is, this term is cutoff ratio, V2 by V1 is 1 by compression ratio, because compression ratio is V1 by V2, the reciprocal is 1 by R, okay, 1 by so that is what I have written here. Okay. So, whole power gamma minus 1, of course, gamma minus 1 will be there, because all these things are within the bracket. So, gamma minus 1 into gamma minus 1 into gamma minus 1, gamma minus 1. So, this is equal to RC by R into gamma minus 1. So, that is T5 by T4. Therefore, T5 is equal to T4 into RC by R whole power gamma minus 1. Now, I have expressed T5 in terms of T4. T5 is expressed in terms of T4. What is T4? T4 from equation number 7 is T1 into R power gamma minus 1 into pressure ratio into cutoff ratio. This I am going to use equation number 7 here. I am so using equation 7 is using equation 7. So, T5 equal to, instead of T4, take the value from equation number 7, T1 into R power gamma minus 1, T1 into R power gamma minus 1 into pressure ratio into cutoff ratio, multiply by this term RC by R in whole power gamma minus 1. See, here we have R power gamma minus 1, here I have denominator R power gamma minus 1. So, that will get cancelled. So, that is equal to T1 into, so this term will, this term and this denominator power will get cancelled. So, T1 into Rp into Rc into Rc power gamma minus 1, Rc power gamma minus 1. Here also Rc into Rc power minus 1, that is Rc power minus 1 is 1 by Rc. So, that will get cancelled. So, this equation will be reduced to T1 into pressure ratio into Rc and Rc will get into Rc power gamma into Rc power gamma. See here, okay. Of course, here also Rc power minus 1, Rc power minus 1 is 1 by Rc, Rc and all will get cancelled. Okay. So, it will be, I have just taken the equation before cancelling this term. Okay. So, this will be the final equation number 8, equation number 8, equation number 8. Substitute 5 which is T2 in terms of T1, 6 T3 in terms of T1, 7 equation T4 in terms of T1 and 8 T5 in terms of T1. Now, I have got T5 in terms of T1 and a few other terms. So, substitute 5, 6, 7, 8 instead of T2, T3, T4, T5 in equation number 4, in equation number 4, and if you simplify you will get this equation. So, this is the thermal efficiency of the dual cycle, that is 1 minus in the numerator I am having, in the numerator I am having pressure ratio into cutoff ratio power gamma minus 1 divided by, in the denominator compression ratio power gamma minus 1 into pressure ratio minus 1 plus gamma into pressure ratio into cutoff ratio minus 1. So, this is the air standard efficiency or the thermal efficiency of the dual cycle. So, with this background we will solve one numerical question like the previous air standard cycles. In a dual cycle, the pressure and temperature at the beginning of compression are 1.03 bar and 30 degree centigrade. The maximum pressure in the cycle is given. Maximum pressure occurs in the cycle at, maximum pressure is P3 equal to P4, that is given as 41.4 bar, and the temperature at the end of heat addition process. Heat addition process starts at, heat addition, see 2 to 3 is heat addition, 3 to 4 is also heat addition, 2 to 3 is at constant volume, 3 to 4 at constant pressure. So, heat addition starts at 2, 2 to 3, then it ends at 4. So, the temperature at state point 4 is given, temperature at state point 4 is given. This is the beginning of heat addition process, this is the end of heat addition process, both constant volume and constant pressure. Okay. So, this value is also given. Assuming a compression ratio of 12, find the total heat supplied per kg of air, fraction of total heat supplied at constant volume and at constant pressure, net work done per kg of air. Okay. So, the pressure P1 is given. Okay. So, let me write, if time is not there to solve completely, P1 is given as 1.03 bar. Okay. P1, T1 is 30 degrees centigrade. The temperature of the air before the compression process begin is T1 is equal to 30 degrees centigrade. So, that is 303 Kelvin. Maximum pressure is 41.4 bar. So, as this one maximum pressure is in point number 3, which is equal to point number 4, state point 3 and the P3 equal to P4. P3 equal to P4 is equal to 41.4 bar. P maximum is equal to P3 is equal to P4 is equal to 41.4 bar, 41.4 bar. Temperature at the end of heat addition process. Temperature at the end of heat addition process. So, if you see the diagram, as I said, heat addition starts at 2 and ends at T4. So, T4 is given. So, that value is 1393. T4 is the temperature at the end of heat addition process, 1393. Let me see, it is in centigrade or Kelvin. It is in centigrade. Okay. So, add 273. So, it becomes 166 Kelvin. Okay. And compression ratio is given. Compression ratio is given as 12. So, R is equal to 12. R is equal to 12. So, for your reference, let me draw the diagram, at least the PV diagram, so that it is easy to understand. So, this is 1, 1 to 2, 2 to 3, 3 to 4 and 4. This is 5, this is 1, 1 to 2, 2 to 3. Arrow mark is very important, 2 to 3, 3 to 4, 4 to 5 and 5 to 1. So, during this both the process heat addition Qs and this is Qr, V5 is equal to V1, V2 is equal to V3. Similarly, here the maximum pressure P max is equal to P3 is equal to P4, P3 is equal to P4. Okay. So, compression ratio is given as 12. So, using the thermodynamic relation between temperature and volume for process 1 to 2, I have used this relation quite number of times. So, T2 by T1 is equal to V1 by V2. So, process 1 to 2. So, T2 is equal to T1 in terms of compression ratio power gamma minus 1. T2 by T1 equal to V1 by V2. Okay. So, or let me write it again. T2 by T1 is equal to V1 by V2 whole power gamma minus 1. So, this V1 by V2 is compression ratio R power gamma minus 1. So, from this we can find T2 equal to T1 into R power gamma minus 1. So, the value of T2 is 818.7 Kelvin, 818.7 Kelvin. Okay. So, find out the volume at 1 like we have done before, P1 V1 equal to R into T1. So, volume at 1 is 0.87 meter cube per kg. So, P1 V1 is equal to R into T1. All the values are known. T1 you know, R for characteristic gas constant for air is known, P1 is known. We can find the volume 0.87 meter cube per kg. So, volume at 1 is found. Okay. Now, using the compression ratio, I can find out the volume at 2, that is after compression, V1 by V2 equal to R, R equal to V1 by V2. So, using this formula V2 we can find V2 equal to V1 by R. So, let us see the value, what is V2? V2 is 0.07 meter cube per kg. This volume is at 2 is equal to V3, okay, because if you see the diagram, V2 equal to V3. So, 0.07 meter cube per kg. We know that during compression process the volume decreases, the pressure of the working fluid increases, pressure of the working fluid increases. The volume stored by the piston inside the cylinder decreases. So, this volume is nothing but V3, this volume is nothing but V3. So, that is what I have mentioned here V2, okay, which is equal to V3. Now, I am going to find out the pressure at state point 2, pressure at state point 2. So, P2 use this relation P2 by P1 equal to V1 by V2 whole power gamma. P2 by P1 is equal to V1 by V2 whole power gamma. V1 by V2 is R power gamma. So, using this relation I can find P2. P2 equal to P1 into R power gamma. So, the pressure at the end of compression is in this, for the data which is given is 33.4 bar, 33.4 bar, 33.4 bar. Okay. So, now let us find the temperature at 3. So, we apply the basic equation for the process 2 to 3, process 2 to 3. Okay. P2 V2 equal to R into T2, P3 V3 equal to R into T3. Let me emphasize again here, for constant volume process or constant pressure process, whether it heat addition and heat rejection process, or even for a constant constant pressure heat addition process, do not use the symbol gamma. So, that is meant only for reversible adiabatic process or an isentropic process. So, divide this equation by this one, R will get cancelled. 2 to 3, we know the volume is constant, volume is constant. So, this term will get cancelled. P2 by P3 equal to T2 by T3, P2 I have found, okay. If you see volume at 2 is equal to volume at 3, okay, volume at 2 and volume at 3. Let us see this one, temperature. One more data is given, the maximum pressure in the cycle is given. So, P3 is given, okay. So, P3 is given, P2 we have found out, T2 we have found out. So, we can find T3, using this relation we can find T3. So, when you substitute the values, T3 will be equal to 1014.8 Kelvin, 1014.8 Kelvin, okay. So, these, though in this question the properties are not to be evaluated at all the points, I am just doing it so that it will be easy for the students to easily understand when you refer it, okay. So, this I have taken a numerical question in all the 3 cycles, so that it covers the maximum on, like what are the estimation of the properties. Heat supplied is given, means heat rejected. So, heat supplied minus heat rejected will give you the net work done, efficiency of the cycle. Efficiency you can use Qs minus Qr by Qs or the efficiency formula which we have derived for the respective cycle. So, T3 is given. Next, for the process 5 to 1. So, for the process 5 to 1, so we can write P5 V5 by T5 equal to P1 V1 by T1 process. For the process 5 to 1, so you can see the diagram, V5 is equal to V1, V5 is equal to V1. So, I am getting T5 in terms of P5. Similarly, take process 4 to 5, 4 to 5 is isentropic process. So, I can use gamma T4 by T5 equal to P4 by P5 whole power gamma minus 1. Let me again recall here once again, if it is temperature volume it is gamma minus 1, if it is pressure and volume it is gamma, if it is temperature and pressure you will have gamma minus 1 by gamma, gamma minus 1 by gamma, okay. T4 by T5 equal to P4 by P5 whole power gamma minus 1 by gamma, okay. So, here also I am getting in terms of P5. So, equating these equation 11 and this one I will get P5, substitute this one you will get this one. So, once you find the properties, now the heat supplied have to be evaluated, that is heat is added at constant volume and constant pressure. So, Cv into T3 minus T2 plus Cp into T4 minus T3. Heat addition commences at 2 and ends at 4 . So, this we know, we have found the temperature T3, T2, T4. T4 we have found using this, okay. T4 we have found using this 750, T5 is 751, T4 is okay, T4 is given in the question. This is T4 is given in the question. The temperature at the end of the heat addition process is given. So, no need to find out. So, when you substitute, you will get the QS as 795.2 kilojoule, 795.2 kilojoule per kg. This is heat supplied, We have been asked to determine the net work done in the cycle. So, we have to find out QR. Heat is rejected at constant volume only. So, CV into T5 minus T1. Okay. T5 I have found using this formula. T5 I have found using this formula, that is 751.9. So, due to time constraint, I am not doing a detailed calculation, since it is already provided in the PPT. So, T5 is 751.8. Okay. So, T5 is 751.8 Kelvin. So, we can substitute, you will get QR, okay. You will get QR. So, here I have calculated QR T5 minus T1, that is 321.8 Kelvin, 321.8 kilojoule per kg. So, QS and QR is calculated. So, let us see the question. Total heat supplied per kg of air. Total heat supplied per kg of air is QS. This is the total heat supplied per kg of, that is question number 1. And question number 2 is fraction of heat supplied, okay. Fraction of total heat supplied at constant volume at constant pressure. So, let us do the part B. Fraction of total heat supplied at constant volume. Fraction of heat supplied at constant volume is equal to fraction of heat supplied at constant volume is equal to CV into T3 minus T2 only, because you have been asked to find what is the fraction of the total out of the total heat supplied, what is the fraction of the heat supplied at constant volume. So, this divided by QS. So, that is what I have done here. Fraction of heat supplied at constant volume, CV heat supplied at constant volume is during the process 2 to 3. So, CV into T3 minus T2 by QS. So, that comes around 17.7 percentage. So, multiply by 100, you will get in percentage 17.7 percentage. Next one, fraction of heat supplied, at constant pressure, that is equal to, that is during the process 3 to 4, Cp into T4 minus T3 divided by the total heat supplied multiplied by 100. So, this should be the remaining 83% or so, because around 18% of heat is supplied at constant volume for the conditions which is given, and here it should be the remaining 83. So, as we when we calculate also, we are getting 82.3. So, that the total heat supplied is 100 percentage. Okay. So, 82.3 percentage. So, out of the 100 percentage, 17.7 percentage of heat is supplied at constant volume for the data given in the problem, and the maximum amount of heat is supplied at constant pressure for this case. However, the percentage will vary when the conditions are changed, And what is the next question is, last one is net work done per kg of air. So, you can net work done is W net is equal to QS minus QR divided by QS. So, QR already I have found here. So, QS is already we have found here, QS 795.2 minus 321.8 divided by 795. So, we will get QS minus QR, net work done is heat supplied minus heat rejected. When we divide this by QS, we will get efficiency. Of course, here for this problem the efficiency is not asked. Okay, so, W net is 473.4, this is efficiency formula, this is efficiency, and in this is the W net, this is the W net. Okay. So, W net is equal to Qs minus Qr. So, 795 minus 321. So, we are getting 473.4, 473.4 kilojoule per kg. So, out of the heat supplied 795 kilojoule per kg, kilojoule of 795 kilojoule of heat supplied for 1 kg of the working fluid, which is air. This in the dual cycle we have got a useful heat of 473.4 kilojoule per kg, while the remaining amount of heat is rejected. So, to summarize this one, of course, though the efficiency is not asked, we can still find out the efficiency using this formula. Only the W net has been asked. Okay, W net has been asked to find. Okay, so this is one. If anybody is interested, we can find the efficiency also, Qs minus Qr divided by Qs using this formula or the formula which we have derived. The answer should be will be the same only. To summarize the contents that we have discussed in this lecture number 9. So, we have started with the various processes of a dual cycle. The other name for dual cycle is dual combustion cycle. This cycle is a unique one in the perspective of the number of processes. From the perspective of number of processes, like it has 5 processes, thermodynamic processes. Most of the thermodynamic cycle have 4 processes. 1 to 2 is isentropic compression, 2 to 3 and 3 to 4 are heat addition process, 2 to 3 is at constant volume and 3 to 4 is at constant pressure. That means first heat is added at constant volume, then heat is added at constant pressure, then the isentropic expansion takes place, that is the power stroke, 4 to 5, and heat is rejected at during the process 5 to 1. In the previous 2 cycles, heat rejection is 4 to 1, here the heat rejection is 5 to 1 because of one additional process. Then we have derived the thermal efficiency or the air standard efficiency of the cycle. In addition to the compression ratio and the cutoff ratio, in the diesel cycle the cutoff ratio is V3 by V2. In case of dual cycle it is V4 by V3, because constant pressure heat addition is process 3 to 4, not 2 to 3. And there is one more ratio, that is pressure ratio, that is the pressure at the end of the constant volume heat addition, P3 divided by P2. So, this is one new ratio which has been introduced in this one, and we have derived the air standard efficiency and solved one numerical question. Though the temperatures and the temperature, volume and pressure are not asked, I mean it has been not asked in the question to evaluate. I have done this one, I have given a detailed procedure. We have been asked to find out the heats, we have been asked to find out the net work done in the cycle, fraction of heat supplied at constant volume, at constant pressure, and of course the total heat supplied Qs. So, with this we come to the end of the lecture number 9. So, thank you. We will meet in the lecture number 10 later. Thank you.
Hello and welcome to this piece of literary snippet. We usually know William Shakespeare as the most revered figure in the history of English literature. But we often tend to forget that he has also been one of the most hated figures in literature. And here I am not talking only about those boys and girls who have to memorize long sections from Macbeth or King Lear or Julius Caesar before they can go and sit for their school or college exams. But I am also talking about people who are themselves quite famous authors. Tolstoy, for instance, considered the writings of Shakespeare to be, and I quote, crude, immoral, vulgar and senseless. George Bernard Shaw absolutely loathed Shakespeare, as he did Homer. But perhaps no other criticism about Shakespeare is more damaging than the one which says that Shakespeare is a marvelous storyteller, provided someone has told him the story earlier. Now, this piece of criticism is particularly damaging because it is true. None of Shakespeare's plays contain any original story whatsoever. They are all written using pre-existing materials, pre-existing stories. Now, does that diminish the stature of Shakespeare as a dramatist? Well, I'll leave that for you to decide. See you in the next episode of Literary Snippets.